Hello friends of .NET, I'm Imo Landworth and you can find me on Twitter at TerraJobst. This is our second episode where we build a compiler from scratch. And today my goal is to add Unary operators. And in order to do that, we will also generalize our operator precedence parsing that we did last week. The other thing that I want to do is I want to add the ability to have conditions. And conditions are interesting because they pose some interesting challenges for our type checker. So right now we just walk the parse tree. So in order for us to actually deal with types, now we have ins and bools, we need to add a new concept to our compiler. So this is going to be a fun episode. I hope you stay around and keep the thumbs pressed that I will actually read the comments this time. So last time I got a lot of feedback that maybe every once in a while I should take a coffee break and read the comments. So today I brought my trusted friend a coffee mug. Hopefully that reminds me every once in a while to check on the comments. All right, then I would say let's just jump right in. So first things first, I want to start each episode, like moving forward, if it's not the first one, but every second episode starting now, we will do some cleanup first, so we actually have a clean code base to work with, because once you're getting carried away, and once you have a week in between, you will probably find some spots that could benefit from some coding improvements. The first things I want to do today is I want to actually add a CI system, because right now we don't have an actual building our project. But before I do that, let me just add a solution file to the root because we currently don't have one, and that is a little bit annoying to deal with. All right, so let's add a new solution. What's it called? Yep, okay, so then let's say .NET, I think it's solution add. Nope, of course not, because we're lazy. All right, that looks good. So now when I say, can I say .NET build actually the solution? Does that work? It does. All right. I guess I've never done that. I usually build with MS Build. All right, let me add this guy, and let me just say git commit add solution to root. And for good measure, let's push that to the server. Then on my DevOps side, let me create a new project so we actually have a build. Let's call this Minsk. Let's make it public so we actually have a chance of handling that. Okay, this thing is doing its thing. Let me actually strip down the project a little bit because we don't need all the services. So we certainly don't need boards because I'm the only guy working on it. Who cares? We don't need repos. This stuff is on GitHub. We do need pipelines. That's where the build is. We do not need artifacts yet, I'd say. Now if we refresh this thing, it looks a lot more stripped down. Now let's actually add a GitHub repo. Yep, how about we add this guy? Startup pipeline, sounds good. And actually, let me go back here. Let me just say, how about we do an ASP.NET Core app? I'd say that's close enough. All right, that looks good. Yeah, I commit directly to the master branch. We are brave. What could possibly go wrong? So while this is running, I can never remember where that was. I think there is some way you can get a badge from that guy, which would be useful to put in our into our README file. Can I do this? How to do this? Maybe I should say edit. no queue. Pipeline. If anybody is online knows how to get the badge, that would be highly appreciated. Otherwise, you will see me clicking around until the build is finished. Okay, the build is green, it's good. You know what? Not the higher order bit right now. But now the key thing is, I think this is set up correctly, so every time we submit a PR, we should also get the build going. So now let's check out a new branch for our work today. Let's call this episode 2, Unary Operators. Sweet. And alrighty. Yeah, so somebody's asking what I'm using with my prompt. I'm using PoshGit, that is correct. No, I'm just using normal PowerShell on Windows. The fact that I just have a $sign instead of the usual stuff is because I'm customizing my prompt to something slightly nicer. But as you can see with my paths here, this is just normally running Windows. There's no magic. I'm using conmu as my console host because I just like that. All right, so now let's do some cleanup. So I was not super consistent last time with my usage of var versus non-var. Somebody called out that there is this handy thing that I'm pretty sure at some point I've actually reviewed the API for that. That just allows us to reset the color. So let's just do that as opposed to remembering the previous color, like people that don't know what they're doing. And I think, if I remember correctly, there was an indentation error here. I think everything is 3 characters, 1, 2, 3. But this one is 4, 1, 2, 3. Yes, this looks slightly better. The other thing that I generally like doing is I like explicit visibilities, not the internal ones. So let's just do a quick pass over our program and actually apply the modifiers that we believe are correct. So we don't need any arcs now because we don't parse anything yet. Let's start here. So here, let's think about the API for a second. So eventually I want to extract all of the stuff into its own class library. Similar to what Roslyn has done, where you actually have an API for your compiler, so you can host it inside an IDE, let's say. So there's certain things you want to have public. So all the syntax nodes you want to have public. So this guy should be public. The evaluator probably should not be public in the long run, but for now, let's keep that guy public. This guy is public. The lexer should be internal because, as you remember from last time, we just call syntaxtree.parse, which is our publicly facing parsing API. And then we get, so this guy should be internal and sealed. I also like to seal my types usually because turns out when you don't design for inheritance, it really works. Or it works in ways you did not expect it to be used, and then bad things are happening. Okay, so this is the last one, I think. All right, let me close all of this. Let me check my notes. What else would I want to clean up? So we did the DevOps stuff. We did the reset color, we did the explicit visibilities. Oh yeah, so in our parser here, I think last time when I created the stuff, I just did not name things in a very consistent way. Let's call this guy maybe match token. That's more in line with what we have. And then these guys, I think, should be the other way around. And then this should probably be parse expression, not parse term. Not that it makes a difference right now, but consistency is a thing, as it turns out. Ah, yeah. the other thing I wanted to do was our syntax kind enum right now is just a sad, sadly placed order. So let's start with something sane. So let's first do the tokens. Let's do the special ones first. Let's start with bad token as the 0 value. Seems reasonable. Then we do the file token, white space token, maybe number token. And then we have the operators. And then we do the expressions. That looks somewhat reasonable. Yeah, the other thing I wanted to do was, so this guy right now is called number expression syntax, but it's really a literal, right? We will later on have other literals, for example, the values true and false are also just literals, or string literals, right, come to mind here. So we'll just call this literal expression syntax rather than number expression syntax. And then we just say this is the literal token. Make things a little bit more consistent. Let's see how we parse this. We just say number token. That works for now. And then I think our evaluator, do we have to rename anything here? Nah, not for now. All right, so then let's commit what we have. Let me see what I actually did. That looks sane, that looks sane, that looks sane. Yeah, I generally like to review before I push. Call me paranoid, but you never know. You never know. Once you are getting carried away with coding, sometimes you do stupid stuff. All right, so now let's commit this and call this some minor cleanup. So let me push this branch so that if case you want to follow along, you can actually clone my branch if you really wanted to. Somebody pointed out that it still is hard-coded to number token somewhere. That is a good call. So let's first create the PR. Let's call this episode 2 changes. Nah, let's just call this episode 2. So this will be my PR that I just keep open and just keep pushing to it. And then every once in a while we might want to check whether we broke the build. Now let's actually check whether the build, oh yeah, the build is going. So that worked. Azure DevOps for the win. And now let's actually check out what somebody said. We still have some hard-coded stuff somewhere in the getter. Yes, we should rename this guy. Good call. This is called literal expression. And then let me be a nice person and actually not just amend my commit, but instead, actually let me do this. Let me actually instead push a new one, so in case you actually pulled this, you don't have to do any crazy resets. Fixed literal, fixed usage of number expression. Actually, let's associate this with the upstream correctly. All right, so I think that is all the cleanup I wanted to do. Actually, no, there's one more thing. Yes, there's one more thing. I noticed that in pretty much all the other compilers, I didn't call this guy next token, but Lex, because Alexa, Lexis, right, seems somewhat reasonable. Let's kill this comment here while we're at it. And yeah, that's the other thing that kind of annoyed me. Let's use the switch statement here. Not that it makes a huge difference, but slightly easier to read. Alright, let me do this. Alright, we renamed this guy, we did the useless comment, and we did that. Okay, some Lexer cleanup. Yeah, so somebody's asking why the syntax kind members all end in token. Isn't that redundant? Not really. So the way to think about the syntax kind is that I use the same enum for both my tokens and my expressions. So there might be cases where these conflict. For example, we had this before with number token and literal expression, right? Sorry, with number token and number expression. Generally they won't, but still I think it's good practice to just say, when you have an enum like this, which basically represents a wide variety of stuff, be consistent in your naming, because then you know what these things are used for. So that would be my take on that. Also, I am heavily biased towards how the Roslyn API works, because again, I actually was part of the team that reviewed the API surface, but I also kind of actually like the API surface quite a bit, and I've implemented other compilers with similar API patterns and found this to be quite workable. When I say compilers, I really mean two. So barely enough to warrant the plural here. All right, so then I think we can jump into the interesting stuff. All right, so let's look at the parser. So last time we added these guys here, which are effectively our expression parser for plus, minus, star, and slash. And they handle precedences by the sheer fact how they're written. Now that's okay if you have like 4 operators. It starts to suck a lot more when you have more like 12, 15, 20. And if you think about all the operators you want to support, I mean, you probably want to support a modulo operator, maybe an and, an or. We want to add Unary operators, or we have plus, minus also as Unary operators. And at some point, factoring things into multiple methods starts to become a little bit unhandy. So what most parsers do, and parser generators have done this also for years, is that you can define effectively a priority or a precedence for an operator, and then you can just shuffle them around, and then your parser is data driven by those priorities, which makes adding new operators slightly easier. It also allows you to look at the operators and see which priorities they have without looking at the parser and trying to figure out in your head what the order might be. So let's try this. So let's write a new method, and then we just see how this goes. So we say, instead of doing this, we call this parse expression, where we say int parent precedence, which is 0 at the beginning. And then we say var left is parse primary expression, I think. And so now we have a primary expression. Now we have to look at the next operator. So let's get a method, private static int get binary operator precedence. Again, that's always great when I can type things the first time. And then we say, we switch over that guy, switch kind, and then we say case syntax kind plus token. What else do we have? Minus token, oops, star token, and slash token. We say this, and then we say default return 0. So the idea here is that if I return 0, it's not a binary operator. So let's say actually while true, var precedence equals that guy for current kind. So if we don't have a current precedence, we break. And then we say return left. Or if the precedence is lower or equal to parent precedence, then we also say break, because then we want to parse it later. Otherwise, we say operator token is next token. Then we say var right equals parse primary expression. And then we say, actually no, we don't say that. We say that is parse expression for our precedence. And then we say left equals new binary expression for the left, for the operator token, and for the right. I think. Now, I think we can get rid of this guy here, as well as this guy here. And then I think we can also get rid of parse expression, because it's now effectively this guy, because the default value is 0. And what are the chances this will just work? 1 times 2 plus 3. Actually, the other way around. 1 plus 2 times 3. 9. That does not look good. Yes, we don't parse it the way we want to. Oh, actually, never mind. We parsed it correctly because our precedences are messed up. Yes, so basically what we want to say is we want to say this guy has a higher precedence, so this is 2. And this guy have a lower precedence, so that's 1. So as again, 1 plus 2 times 3, 7. Yay! That is nice. Yeah, Frank says this is tricky code to write and we're brave to do it on air. But also I think the benefit that I have is that I'm generally not easy to be embarrassed. The benefit of once you're messed up is that you don't really care anymore. All right, so then we have that, which I think is kind of where I wanted to go with this one, and now we can actually push that. Let's call this git commit make precedences data driven. Actually, let me do this because there is no way I typed this correctly. Might as well use an editor. Make precedences data driven. All right. Let me push that for other people to consume if they want to. All right, so one thing I want to do is I don't want to have these guys floating around here in my parser. I mean, you could argue that they belong here, but I think I want to follow what Rosin has done. And I have for now an internal static type. What type? Type is not a keyword. Syntax kind, no, syntax facts. What am I thinking? Which will basically be our type where we store all the information about the syntax in a singular place. And then instead of doing this, we say, actually, let's be cute here. Let's make this an extension method, because why not? We can. And then we can just say kind get operator, get binary operator precedence. All right. That looks good. Okay. Okay, get commit. Move precedences to syntax facts. All right. All right. It looks halfway decent. Okay, now let's think for a second about unary operators. So let me do my usual diagram. So unary operators are things like this, right? +1, -2, so -1 times -3, right? Things like this. And of course you can do minus these guys, right? So basically there are operators that are leading a singular expression. Again, the parse tree is somewhat straightforward. Let me actually create some space here. Let's start with 1, right? This would look like this. You just have a singular node whose child is the expression that you're negating. And then let's do one more that is a bit more the constructed case. So we have, let's take the last one. So we have plus, let's make this. And then let's say we want to negate this guy. That would look like this. So that is kind of the trees we're trying to construct here with unary operators. So let's first define the actual syntax representation for that. And since I'm lazy, let me just copy the binary operator. Let's call this Unary Expression syntax. In our case, we just have an operator token, and then we have, let's call this operand. Not that it makes a huge difference, but. And yeah, let me make this immediately this guy. And then we call this guy, what do we say, operand. And then we can actually initialize this. And let's see what I actually want to return this. We need an inner member for that. And in this case, let's actually put this right where we want to put it. And let's move this to its own file. All right, so now we have our unary expression syntax. Yeah, let's actually fix this guy first, because otherwise I will debug a crash later and have no idea what happened again. Unary operator, in which case we just say var operand equals evaluate expression for node dot no, not node, u operand. And then we say if, what is it, u operator token kind equals syntax kind minus token. We just say return minus int, actually we don't have to cast yet, evaluate expression for, no, actually what am I doing? Minus operand. I already did that. Maybe let's start with the plus token, because the plus token doesn't do anything. And then we can just say, if we don't know what it is, actually again for consistency, let's do this. And we say unexpected unary operator, u operator token kind. All right, so far so good. Now let's actually handle this in our parser. So where would we put this? So logically it belongs somewhere in here. So what we want is something along the lines of, yeah, we need a, first let's go to syntax facts. Let's add a new unary operator precedence. In our case, we just have this guy. So what's interesting here is that they interact, right? So you want to have precedences spanning both unary and binary operators. Because if you have stuff like this, right? So if you have minus 1 times 3, right? So you can parse this in two ways. You can say, I can say, I have the minus at the very top, and then I have the multiplication below that. Right? That's one way to parse it. The other way would be probably what you would expect, because that's how math usually works, is that this guy is like this, right? And so what controls whether you get the top parse tree or the bottom parse tree is the precedence relationship between star and minus. If minus binds, like if the unary minus binds stronger than this guy, then you get the bottom one. Otherwise, you get the top one. I hope that makes sense. So what I will do is I will just say there will be 3, which is the highest precedence we have. So these guys bind stronger than these guys. Somebody says, keep the tree comments. Yes, yes, yes. That's a fair point. All right, so let's go to our parse expression. So this is going to be here. So how do we do this? We say Unary operator precedence is current syntax kind get, what did I do? Oh, because I'm an idiot, it's kind. And we do the other one, right? Yeah, we do the other one. All right, so then we say if Unary operator precedence is not this, and the Unary operator precedence is stronger than this guy, then, yeah, first of all we say expression syntax left. Then we do this. Otherwise we say var operator token equals next token. And then we say var operand is parse primary expression. Actually, that's probably wrong, because we need to support multiple well, let's leave this for now and say left equals new Unary expression syntax for our operator token and our operand. I think that's right. What are the chances that this is correct? All right, so let's try this. -1 is -1. That's a good starting point. +1 is +1. Let's see the trees for that. Yep, that makes sense. So we can say -2 times 3, hopefully. All right, that actually does work. Now let's say whether this works. I'm impressed. Does this work? Nope. Unexpected token minus token. Yeah, that doesn't work because we didn't make it work. Yeah, that's right. So, I mean, strictly speaking, we should be able to just say this, right? Because that's how precedences work. So we pass in our current precedence. Maybe that fixes it already. Nope. That's funny. So if we have 1. Okay, that seems more like it. Plus, minus, minus, plus 1. So plus, minus, minus, plus 1. Yep, seems all right. I mean, if you ever write math like this, you should be shot in the head, but it's nice if you can parse it. The only thing that throws me off a little bit is that we have these guys in the opposite order, but I guess that is what you would expect. Yeah, because technically speaking, yeah, I think in this case it makes sense that they're the other way around. I can't explain this, but that's what it is. All right, so let's say we have this. Now we have Unary Expression syntax. We added this guy, added the precedences, added this entry here. Let me commit this, and then let me go to questions. Add support for Unary Operators. Is it optimization time yet? No, it's not. I think I know the person who's asking this. Tim, don't be a troublemaker. It's hard enough to write the code. Somebody asked, I wonder what it's like to understand this. So I hope that I do a decent enough job to describe it. If not, ask pointed questions. Any plans to support postfix? I have not supported postfix in our in the finished product yet. I can probably add them though. I think the way you would do postfix operators is you would probably put them somewhere between parse expression and parse primary expression, would be my guess. Or would you? Yeah, I guess somewhere in between. All right. So then, yeah, I think it's time to talk about how type checking works. So let's just quickly reflect on where we are and what we are actually doing here. So if we look at our program file, the way the thing currently works is that first we parse and we get back the parse tree. And when I say tree, if you ever read about compilers, you probably have heard the term AST or abstract syntax tree. The difference between abstract syntax trees and the trees we have here is literally the word abstract, and that's for a good reason. So when you think about a compiler, right, a compiler generally doesn't care about white spaces, it doesn't care about comments, it doesn't care about things like parenthesized expressions either, because the way you express parenthesized expressions is just by the way the tree is shaped, right? So in the resulting tree, parenthesized expressions are effectively dead weight. All they do is they just control how your parser traverses the input, or I guess what tree you construct from traversing the input. The thing is, you don't want this in the type checker because you don't care about this in the type checker. But if you write tooling, let's say an IDE, for example, you do care about white spaces and comments, because turns out when you do things like refactorings or code analysis where you want to put squigglies all over the place, you want to do this in the context of the original document. So you want to know effectively, okay, this is line 100. And that's okay if you just record the fact that it's a line 100, but now think about what will happen if you want to modify the text. Like say you want to actually do a refactoring like rename identifiers, or take a binary operator and swap the sides or something like that. It is so much easier to do if your trees actually contain the entire input as part of the tree, because then all operations are expressible over the tree. And so this is why Roslyn went down with the actual concrete syntax trees, and Ours are not complete yet, so we don't actually include white spaces and comments yet. I will talk about how we can do that later. But for the time being, let's just say our syntax tree is a representation of the input file at full fidelity, right? It's not true, but true enough. The other thing that we have, I haven't talked about this either, but it's kind of like implicit by construction here, is that our entire thing here is immutable, right? So there are no setters, there's only getters. So the idea being that once you have a syntax tree, it never changes. And again, like in a normal compiler, when you compile on the command line, you generally don't care because your compiler on the command line is doing everything at once, right? And then writes the output file. But the point is that in production environments like IDEs, you generally do compilation, if you will, all the time, because every single time you're typing, you expect the type checker to do its magic. And in that environment, you generally have multiple threads going, things running background operations, and having an immutable representation there is super beneficial because you can reason about your system in terms of inputs and outputs that never change. As soon as you have syntax trees that get modified, let's say incremental parsing or something, and now you have to like have flags on those and say, okay, what information is valid, what is not. It's a world of pain. And as soon as you have flags and states, you probably have locks, and when you have locks, you have deadlocks, and not a fun world to be in. So we want to make our lives easier so everything is immutable. Now the downside is, if you look at our, for example, binary expression syntax, we only know the things that we can know from parsing, right? So we don't have any sort of information about the types. So we don't know, like the left-hand side, what type does this resolve in, right? Because there's no place to put it. In the normal compiler design, when you have abstract syntax tree, the idea is that the abstract syntax tree just has a variable there, like a slot for the type, and then your later phases, like your type checker, just fills them in, right? And that's basically what I mean by you have state that might not be valid at all times. And so the way we do this here is we just create a new tree, and we just follow the conventions that I picked up from Rosen, and we call this the bound tree. So you may have heard different terminology for that. A very common term for that is also intermediate representation, or annotated ASTs, or in our case, we just call it the bound tree. So before we do that, let's just push all the stuff we currently have that is dealing with syntax into its own sub-namespace. So that's a bit easier to reason about. So we call this syntax, and then we just take, I guess, everything but the evaluator and shuffle that in here. And then for good measure, let me fix the namespace. Yeah, which is not going to be sucky at all. So someone from the Rosen team is watching. It would be super nice to have like a right-click, fix my namespaces to match my folder command. Just saying. And don't you dare tell me you accept pull requests. I know that. All right. All right, bunch of busy work. Now I guess I need a bunch of usings. Oh my God, there's this. Who does this? No pun intended. And then this guy needs a using as well. All right, let's see what we did. So we renamed a bunch of files. We modified this guy, we modified this guy. That looks about right. Move syntax APIs to separate namespace / folder. All right. So far, so good. So far we have done nothing. I talked a lot and we put some stuff in a folder. Now let's create a new folder here parallel to our syntax folder, and let's call this the binding. And let's add a new thing here, which we will eventually need. No, not a folder. What am I doing here? Delete. I want a file in this case. Yes, delete permanently. Binder.cs. And let's call this namespace. Actually, I am so lazy today. Let's call this binding. And so everything in here will be private for now, or I should say internal. Internal abstract class bound node. So we will have multiple bound nodes, and again, similar to our syntax, we will have a bound node kind, which tells us which node kind that is. Yeah, this will be an enum, internal enum bound node kind, empty for now. And so we will have a new node here, internal sealed class bound expression node, which is a bound node. Actually, it's not sealed, it's the opposite, it's abstract. And this guy will add one more concept here, namely, what type does it result in? And for now, we don't have type symbols in our language, we just use our trusted .NET type representation. Eventually we will fix that too, but one step at a time. I can only type so fast. All right, so we have bound. Let's call this Unary Expression. Yeah, it's actually removed the node here. That doesn't add much here. And this one will have, yeah, what do we take? So we clearly take bound expression operand, but we also need some sort of internal enum bound Unary Operator kind, which in our case we only have two right now, which is, let's call this identity and negation. Let's call this guy operator kind. And then I guess we say type. For now we just say it's the same as our operand type. That is probably not holding in the long run, but for now that's good enough. And then we say this guy is bound node kind Unary Expression. I should probably add the simplest one first, actually, now that I'm thinking about it. Internal sealed class, let's call this bound literal expression, which is a bound expression. And then this guy is public, let's call this object value. Oops. So this guy is bound node kind literal expression, and then we just say the kind. Actually, no, not here. Here we're saying this, and then the type is value get type. So we expect non-null values here for now, because we don't have a null literal in our language anyway, so all good. Yes, we need that guy. And then let's do one more, which is the binary one. Bound binary expression. We need a bound binary operator kind. And then we say we have a bound expression left. We have a bound expression, let's call this right. Let's call this guy right. And let's do this. Let's return left dot type. Again, this is probably not what we're going to do in the long run, but good enough for now. And then we say we have an internal enum. where we have, what is it, addition, subtraction, multiplication, and division. All right. All right. So far, so good. Now we have all of this stuff that we just created out of thin air. How do we create these guys? Well, the idea would be that we have a new type which walks our syntax tree, and we call this guy the binder. And so the binder's job is effectively what the type checker would do. So the public method is public bound expression bind. We take an expression syntax, and we call this syntax. And now we do a switch statement here. This is actually where these guys now finally start to get handy. So we say case syntax kind. What do we have? We have a binary expression. We have a unary expression. We have a literal expression. I think these are the only ones we have for now. And we just say this is return bind literal expression for. We cast this guy to literal expression syntax syntax. And then we just say, did I not spell this correctly? Literal. No, I did not. As it turns out, I did not. Which is kind of a bummer because that would help my copy paste. Here we go. Binary. And then we say default is throw new exception unexpected syntax kind. All right. Now we add these methods here. So what do we have to do in order to bind literal expression? Well, we say var value is syntax dot value, what is it, syntax literal token value. So if this guy is null, so we say this guy is, what do we do, as int question mark, and if that is null, we say 0. And then we say return new bound literal expression for syntax, for the value. So if this guy is not actually, I think this can be null, because if the parser had to insert a number token, we already reported an error, so we just return 0 here. So for the unary expression right now, we just say var bound operand. This is where the recursion comes in. We say bind. Yeah, we should probably call this bind expression. Bind expression for syntax dot operand. Then we say var bound operator kind is bind operator kind. I guess bind unary operator kind for syntax dot operator token dot kind. And then we say return new bound unary expression for bound operand, for operator kind, and for bound operand. Let's do it the other way around then. And this one looks pretty similar. So what we do here is we say bind binary operator kind, and then we say this is left. So we say this is bound left. Instead of right, we say bound right. And then we say this is a binary expression for bound left, bound operator kind, bound right. All right, let's create this method, and let's create this method. So this guy returns a bound Unary operator kind. This would be that guy, and this guy returns a bind binary operator kind. That would be this guy. All right. Now we say again switch kind, and we say case syntax kind plus token. We say return bound Unary operator kind identity. And we say minus token is minus token. No, what? Negation. And then default we blow up again because we don't know what to do. Throw new exception. Unexpected Unary operator. All right, so let's call this would be addition. This would be subtraction. And then we say this is what? Star is multiplication, and this is division. And just for diagnostic purposes, let's do that guy. All right, so now this is not quite correct. So basically what we really want to pass in here is actually the operand type. And this is why I think I had it originally the other way around. So because we need to select for the particular type, right, we pass in the type here. So logically what we want this guy to do, we say operand type. And then maybe we make this guy nullable. So we basically say if operand type is type of int, well, I guess if it's not typed of int, then we say return null, because we have no idea what this is. Same thing here. So we say type left type, type right type. So if left type is not int or the right type is not type of int, then we have no idea what this is. So we say bound left type, bound right type. And this is where type checking kicks in. All right, now we also have to add diagnostics because the binder, the type checker might actually not work at all. So let's do this list of sometimes I hate IntelliSense. List of actually let's make this read only list diagnostics new. Yep, that guy. Yep, add the using. And let's have a public one, enumerable of string diagnostics, returns the underlying diagnostics. Sweet. Now we say here, if bound operator kind is null, then we return, then we just say return bound operand. And we say diagnostics add Unary Operator syntax operator token text is not defined for type bound operand type. Value. So same thing here. We say binary operator is not defined for types bound left and bound right. Let's add a period at the end. Not that it makes a huge difference, but it just reads slightly nicer. We say bound left. So why are we returning anything here? So the idea here is we return something so that nothing null references. And you all want to do something better moving forward, because otherwise you get cascading errors, right? If types don't align, then you just get errors after errors after errors. But let's not worry about that for now. All right, so now we have the binder and the bound node representation. So the first thing I want to do is I want to change my evaluator. So instead of walking the syntax, we now walk the bound tree. In fact, before I do that, let me read the comments. Somebody is asking why Minsk. Very simple.
Have you ever considered Minsk?
Yes, all right, so no more question for this one. So let's just walk our bound expression representation here. Instead of doing this, we of course need this guy now. Now we say bound expression. Let's call this bound expression. No, what is it? Bound literal. In this case, we just return the value. If it's a bound unary expression, then we say, what is that? Operator kind. In fact, let's make this. Oh, it can't, because now it's messed up. And this would be bound unary operator kind. And we call this guy, what is it called? Negation. Identity. And then we call this just a operator kind. Make this a switch, slightly easier to read. Let's make this a switch as well. It also means you have less things to do. Bound binary expression. Operator kind. And now we say bound node, no, bound binary operator. Bound binary. Ah, damn it, I just type it out. Bind, and by typing out I really mean I type it out. And then we say this is addition. And then this is subtraction, this is multiplication, and this is division. All right, this guy we no longer need because we don't have parenthesized expressions in our bound tree. Yeah, that's a good point. I guess this guy is internal after all for now. That works for us right now. All right, so now let's go here. So we parse this guy. So first of all, before we do anything, let's actually extract these guys. And we call this diagnostics. Put this guy here. Then we say we need a binder. Var binder equals new binder for nothing. And then we say var bound expression equals binder dot, I guess, yeah, you can't have IntelliSense if you don't know what's going on. Bind the syntax trees root. And then we say our diagnostics are the syntax trees diagnostics concatenated with the binder diagnostics to array, because why not? What are you talking about? What? Did I not spell it correctly? No, I did. Oh, I did include the wrong namespace, didn't I? Yes, I did include the wrong namespace. Why would I do that? I want to use my own. Yep, because it's bind expression. Alright, so far so good. And now we just say, instead of doing this, we do this. What are the chances this will just work? Wow, I'm amazed. I did not expect that to work. All right, so far again, we have done nothing realistically. We just have added this new concept of the binder. And create a bunch of new nodes. So before we do anything further, let me just split this, I think, into the corresponding files. And then we can talk about how we add some new concepts to our language. So again, if somebody from the Rosin team is watching, I would like to have this operation for the whole file, because quite frankly, I don't want to walk the types by hand. All right, so far so good. I think it's time for me to commit. Let's call this add binder. Yeah, Frank is saying amend the previous commit. Did I? Yeah, I could have, but the problem is when I do that, everybody who's pulling right now gets bad. So far so good. Everything was building. I'm actually amazed. All right, so now let's talk about adding some new things to it. So I want to add booleans. So the way I will do this, so first let's actually go to our where should I start? I probably should start in the lexer. That probably makes the most sense. And so we say, so basically what I want to do is I want to recognize true and false. And so the way I do this, I will say if char is letter current, we basically do this. And then I say the kind is syntax facts get keyword kind for the text. So the idea being that, the keyword recognition is just handled in some centralized place. Okay, let's add this method. This is syntax kind public. So we just say switch text. So Our language is going to be case sensitive for now. You may want to change this later to be case insensitive. Syntax kind true keyword. And we say false. False keyword. Otherwise, it's just some rando identifier. So we also don't have the concept of identifiers yet. Identifier token. But we will add that. So let me do this. So let me add that guy here. And then let's have a new section called keywords. And then let's have false before true. Not that it matters, but it seems more logical. Yeah, I think that one will work for now. All right, now in the parser, when we parse an expression, let's do this and say else if current kind equals syntax kind true keyword. False keyword or true keyword. And then we say var value is Boolean. And then we say return new literal expression syntax for the current token and the value. So right now we don't store a value. Right now we assume the value comes from the token. So let's do that. Let's actually add that guy. So now, what is it again? Find all references, Shift F12. Let's see who's using that. The binder is using that here, right? So instead of doing this, let me say this. You're using this. You're using this. Good enough. So now let's go to the little expression again and fix the constructor. Let's actually add another overload that effectively just does this literal token and literal token dot value. I could have also just made the value on token settable, but let's not make things mutable if we don't have to. All right, so now I have that. Let's actually see what happens now. Oh, yeah. So if I do this, this will probably immediately crash. No, it's worse. It doesn't even parse. What is happening in my parser? Why is that not parsing? False keyword, true keyword. Oh, because I'm an idiot. Var keyword token is next token. Remember when I said make sure your parser always consumes tokens? Yeah, about that. And then let's make this a switch. Makes it slightly easier to read. God, who came up with this brilliant idea that these should be formatted like this? All right, let's try this again. Now I think it will crash. True. No, actually I cast. Good call. So this is, so because it's not an int, we do the try cast in the binder, right? That's why we return 0 for all of those. So let's first change our binder or sorry, our evaluator to actually deal with arbitrary values. So instead of int, let's just make this object. And then we can just return this guy here. So if we get here, it needs to be an int. Otherwise, something bad has happened. Same thing here for now as well. So this at least allows us to do true. That is funny. What is happening here? Oh. Did I mention I'm an idiot? I think I did mention that. So at this point, so let's do it this way. If syntax value, actually let's do it like this, right? There we go. That seems more like it. All right, now we at least have these guys. Now if I say minus false, nice, I get now a type check error that says Unary operator minus is not defined for Boolean. If I say true times 4, it says binary operator star is not defined for types Boolean and int32. False times true. Binary operator is not defined between bool and bool. Nice. So that seems like a good way to start this. I don't think there's any more questions regarding the type checking. All right, so I think we can now say we did at least some. What did we just do? So we added, so we fixed this one. We made us evaluate these guys, so yeah, so let's call this and say add support for Boolean literals. Good enough. Good enough, I'd say. So now that we have that, let's talk about some more operators. So one thing we want to do is we want to support, let me actually go here. Where would I first do that? Actually, let's go to the Lexer first. So the first thing we want to do is we want to support a few more operators. Specifically, we want to add support for not. All right, so we say this is the, let's call this the bank token for now. And then let's add support for these guys. Now, yeah, I can do that obviously. So do I have a look ahead here? Do I have a peak? I do not have a peak. So let's add the peak first. Let's call this peak int offset, similar to the parser. Var index equals position plus offset. And then we can replace this guy with index. And then we say we have a current, which is just peak 0. And then we say we have another one. look ahead, which is a peak 1. So let's do this. I can say if look ahead equals this as well, then we do this. Otherwise we just fall through. And then we say this is the ampersand token plus equals 2, and that would be this guy. And we do the same thing for OR. And this guy would be the pipe token, let's say. So let's do this, let's do that, and let's do that. And while we're at it, let's put them, maybe actually want them maybe here. Seems reasonable. All right, so this way we actually parse, or lex I should say, these guys. So if the next one isn't, it just falls through here, and then we'll just return a bad character and input. Is that all we needed? I think that's all we needed, right? Yeah, now let's talk about how we parse them. The nice thing with our parser now is that it's priority driven, so adding new operators is pretty straightforward. All we have to do is we have to decide which priority they have. I think they should be lower than, so what do we have? Ampersand, and we have the pipe. Generally speaking, I think we want pipe to bind less strong than ampersand, because that's basically AND, right? So you want AND to bind stronger than this, but you don't want to bind it as strong as these guys here, I think. So let's just number them correctly from the bottom up again. 1, 2, 3, 4. This guy is then 5. All right. Now we have to say another Unary operator, which is the bang token, which I don't think we care how strong this binds regardless to the other one, so let's just put it here. That seems reasonable. All right, now we can parse them. Now we have to bind them. So let's start with the bang token. So we say if the operand type is int, let's do that. In fact, maybe I shouldn't throw an exception here, but just let it fall through. I think that is probably the right behavior anyway. Yeah, let's do that. Here's a handy trick. So I can just do this. Put this guy in here. And now instead of me fumbling around with the expression, I can just say invert if. And then booyah. Again, fall through. All right, so now let's add one for bool. If it's bool, and we have a, what is it, the bang token, then we say this is yeah, let's call this logical negation for now. Logical negation. So let's add this guy. Same concept here. We say instead of this, we say bool. If it is ampersand, ampersand. If it is pipe, pipe. we say this is logical and we say this is logical or. So let's do that. Okay, now we are type checking these guys. Now let's check whether we evaluate them. Evaluator. So instead of doing the cast here, let's just push the cast into here. This way, it's a little bit easier. We can just say inline logical negation. This would be a bool. We negate it. And then we say binary expression, same thing here. Let's put these guys here. So this would be left plus right. All right. So we say this is a logical AND. So in this case, this would be this. And instead of doing this, we would say cast a bool. And then we say this is logical OR. And then we say logical OR. All right, let's see where this leads us. To not compiling. Invalid expression term. Where the heck is that? Lexer 18. Isn't there? I can never remember. What is this called? Toggle panel, or whatever it's called. Yeah, how do I get this guy in the bottom now? No, I don't want multiple windows. Yeah, that's what I want. Here we go. Oh, I messed up. All right. That should do it then. Yeah, it's actually, was that output? Oh, I don't remember. Anyway, so 1 plus 2 times 3 is 7. True and false is false. True or false is false. True or false is false. This can't be right. So we parse it correctly. What is happening? Logical OR is left, right? Probably bind it incorrectly, right? Bind binary expression kind. Nope. Bound binary operator kind logical OR. What is happening? True? True is false. Okay, that explains that. Yes, I know what the problem is. Parse primary expression. Yes, I need to do this. Yes, 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 yes. Correct, Frank. You got it. False, false, yes. So that means now true and false is false. True or false is true. And if we say true or 3, it says doesn't work. All right, so far so good. Now, what happens if I do this? bad character and input. All right, that also works. So we are pretty good. So now let's say, let's get these guys in. And let's call this git commit add support for all right. So far so good. So we now have basic support for conditions, but the most common one you want to have is double equals. I think you want to be able to do that. But before we go there, we need to change our binder a bit to be a bit more data driven with respect to operators. So as you remember earlier when we said binary unary expression, we said the type of the unary expression is just whatever the operand type was. That might not actually be true, because you could imagine operators that actually change the output type, right? So for example, equality might be defined between two ints, but it returns a Boolean, right? So same is true for binary expressions. Right now we just return whatever the left type was. But really what you have to return here is whatever the type of the operator is you are binding to. And right now we don't have a representation for this. All we have is this enum here, and that doesn't tell us a whole lot about the operator. So let's start by introducing this concept of an operator, actually. So let's say we have a binary sealed class. It's called this bound binary operator. I think I will have this as a regular table for now, so I don't think I want a public constructor. So I will say kind. In order to make my own life easier, I will probably bind it to a syntax kind. And I would say, well, you have an input type, operand type, and you have a return type, result type. Oopsie. Which, actually that's not binary, that's unary. Let's start with unary. And then we say, okay, yep, we need a using for that. And then let's just add these guys. And then let's also add another constructor that doesn't actually have a result type, which is for the easy cases where they are the same. So we just say this syntax kind, operand type. So now we say we have a private, static, bound operators. Let's just do this one now. So we have a bound syntax kind, what did we say? Bang token. That is a bound unary operator kind, logical negation, and it is defined over bools. Then we have the plus token, which is identity, and that is defined over int. And then we do the same here. We say, whoops, negation, that is the minus token. And then we say private, public, static, bound operator, bound unary operator, bind, and then we pass in this syntax kind, and we pass in the type of the operand type, and then we just say for each var op in operators, if op syntax kind equals syntax kind and op what do we say, operand type equals operand type, then we return this guy. Otherwise we say return false, no, return null. Alright, that seems reasonable, so let's move this to a separate file. Now let's do the same thing here. Let's call this bound actually, yeah, let's go with this one now. Let's not be so this would be it would say type left type right, actually let's do this here, left type right type, this is a bound binary, and then we say initialize this guy, initialize left right. That seems reasonable. And then of course we have an array of those guys. So what do we have? So we have a plus token, which is associated with the addition for int. So I think I want a convenience overload that will probably yeah, I think I don't need, so I mean, definitely need one that just says type, and then all it does, it says syntax kind, and then it uses the type as a left, type as a right, and as a result, because that's basically what our ins are. So what is that? Minus minus token, star token. Yeah, let's add the using here so we don't fumble around so much. Slash token. So this is subtraction, multiplication, division. Right. So now we have the same with bool, where we say we have the ampersand token, which is logical and, logical or, and then we say pipe token, and then we say we need the left type, right type, and then we just say left is left type and OP right type is right type. Then we do this. All right, let's move this guy to a separate file. Now, of course, our binary expression, instead of taking the kind, it should take the operator. And since operator is a keyword, I will just make my life easier and just call this So stuff will probably not compile now, which is actually what we want, I think. I do the same thing here. I just say this is no, not here. Binary unit expression here. We say this is OP. This is OP. take in this guy. All right, so now our evaluator has to change. We can just go over the kind for now. And then I think the only thing has to change is the binder, right? So yeah, instead of doing this, we're saying now binary, no, bound binary operator bind the operator token kind for this guy. Why does this not work? There's no argument that corresponds bind. Oh, because I'm an idiot. Bound Unary operator, obviously. So we call this say this, and then same thing here. We say bound binary operator bind. We call this bound operator. All right, so far, not horrible, I'd say. Let's quickly check that we didn't break anything substantial. All right. So we have done nothing except that we've just slightly reorganized how things are. So let me just commit this. Yep. Let's call this make operator oh, actually, there's one thing we should probably do, just for cleanup reasons. Get rid of these methods, because they're no longer needed. So we have these guys now deleted and say replace switch with operator lookup. So any questions? Unit test not found exception. Yes, eventually we may have some unit tests too, but I want to get some more basics up and running before we so why don't we merge to get Unary operator precedence and the bind operator precedence methods? The reason we don't do that is because we have the same token, so I don't know how you would do that. So if you go into the parser here, no, not the parser. Let's actually go here. So the problem that I have is that the plus token is a binary operator with a precedence of 3, but the plus token is also a unary operator with a precedence of 5. So I don't know how you would do that. So I don't think you can do that, would be my guess. At least I have no idea how you would do that right now. All right, so now let's actually add equals and not equals. So let's start like we did earlier. Let's add this guy and say we have this guy. We call this the equals token. And then we also have the not equals token. bang equals token. Do we want them here? Probably not. Probably more like here. All right. Interesting. This is why switches are useful, so because they actually tell you what's going on. All right, now we have to go into our syntax facts and make sure we know about this. So we have to decide what priority we want to give those guys. I'm inclined to insert them somewhere here. So we say equals equals token, and we say bang equals token. So that would be 1, 2, 3, 4, 5, and that makes those guys 6. Right? Right. Now, in order to bind them, we need to obviously define those. So let's go into our operator here. So we say they are defined for equals equals token. We say this is a bound. Yeah, actually we need this, let's say equals. And now I need another overload. I think I want to say in this case it's type and result type. Let's call this the operand type. And then we pass in the result type here. So this is accepting of those, but it returns a bool. And then we say we have the bang equals token, which will be not equals, which doesn't no. Why would that be in parameter? What are you talking about? Equals, not equals. Yeah, no idea why I want to make this a parameter. And of course we can define them over bool as well, in which case the definition is a little simpler. Okay, now in the evaluator, I think we can just cheat, because the nice thing with equals is that we don't actually care about the type. So we can just say equals is equals for left, right? That's the static one, right? Yes, that is the static one. And then we can just say not equals. Well, it's not equals. So, yay! Yep, I'm pretty sure that means our priorities are not quite the right way. So let's go to the syntax facts, because I think we probably messed up the priorities. Ah, that's right. We want it the other way around. We want these guys to be... No. What? We want So this is the least priority, this is the second, and then this is the... Yeah, that seems about right. Interesting. So what does this parse to? 1 equals 2, and 2 equals 3. So this is a binary expression. Oh no, it is parsing correctly. Of course, I've messed up my binder here. So remember what I said earlier when I said we returned the wrong results here? Yeah, we need to return the correct results here. So this is op.type, or operator result type. And the same is true here. Instead of returning the operand, we say result type. Right? Right. But for consistency reasons, let's actually call this type. And same here as well. So now, if we actually run this, it should actually produce the correct result again. So I would say 1 equals 2, or 3 equals 3. It's true. Yeah, doesn't matter. False. All right. That binds the way it should. All right, I think that's it for today. At least for my list, I covered everything that I had planned to cover. Any more questions? Otherwise, I'm inclined. I probably should commit, right? Yeah, I could try to split this into 2 commits, but life's short. I'm not feeling like it. Let's say this would be add support for equals and non-equals. Also fixes an error in the binder that doesn't correctly compute the resulting expression. It should have used the operator type, but still uses the hard-coded operand left resulting types. Good enough. How does it look like here? Everything seems to be bullying there as well. Yeah, as far as I can tell, there are no more questions. So we did a bit longer today than I was hoping for, but I think that's a pretty good lineup that we have. So to recap, what we did today was we added the new concept of a binder, which is our type checker that walks the tree, computes the resulting type, looks up stuff. And this is where we'll in the future add more complicated stuff like looking up identifier names, dealing with scoping, dealing with variables, dealing with constraints on variables, that basically tells you maybe the variable is read-only or it's read-write, that sort of thing, right? The second thing we've done is we have generalized our operator framework a little bit more. It started with the parser where we added the precedences, so we can add more operators in an easier way. And we also changed the way we resolve operators and bind to them in a more data-driven way as well, so we can actually express different input and output types and have that make sense in the rest of the system. All right, so then I would say, give the video a like if you liked it. If you didn't like it, feel free to dislike it, but I would really appreciate a comment where you could tell me like why you didn't like it, so I maybe have a chance to improve for future videos. Other than that, I'd say thank you very much for listening in, and then hopefully I'll see you next week. Bye bye.